Hello guys, welcome to our YouTube channel VLSI Chaps, and today we are back with another interesting yet the prominent topic in the field of electronics and communication systems. Yeah, you guessed it correctly. As you can see on the screen, our today's topic is embedded systems. So let's get started. Now first question comes into our mind that what is an embedded system? To understand that, let's first divide this whole word into a fractions. What is embedded first things? So what we can think of is one thing which is attached to another thing, that is called an embedded. So here what are the things? These things are nothing but the hardware and the software. So what we can think of an embedded system is a software which is embedded within the hardware, right? But that is not the complete definition. Why? Because in that particular hardware, there are various modules. Each and every unit or the module is designed to do one specific task or job. And because of that, all these units are assembled in a particular manner or a fashion in which they all can work together and make one particular system. So once these all hardware units are combined, it becomes a system. And because it is a software embedded within that particular hardware, it is called an embedded system. Now let's go one step deeper. In this embedded system, we talked about hardware and software, but that is not the two integral layers within that. One another layer is added which is called firmware. So if we see the hierarchy, it is first hardware, then firmware, and then the software. So software is the top application layer in which we as a user install or uninstall various programs in our operating system. They are defined to do one specific task, correct? Those softwares we can change very often. There is no restriction over it. If we talk about the second layer, firmware, then this firmware is also kind of software, but in that we are writing a set of instructions, and this set of instructions will define the behavior of that particular hardware in which it is flashed or in which it is used. So what we can say is this firmware is not that oftenly changed, because as it is linked to the hardware, we cannot change it that often like we change our softwares. And talking about the third part, which is our definite hardware, in which there are various components or building blocks. And of course, this hardware is not that frequently changeable, because once the design of that particular hardware has been completed or finished, the redesign cost or the changeable cost of that particular hardware is quite huge. And once this product has been developed in bulk, its cost is quite high. So we can say that this change in the hardware is nearly zero. So what we can think of is this whole combination of software, firmware, and embedded creates a whole embedded system. And can we say that this firmware is the bridge between the hardware and software? Because that is the core system which is able to decide the particular behavior of that hardware, or can say the whole system. Now if we talk about the primary task that a particular embedded system is supposed to do, then it includes three various tasks. First is receiving the information. So any embedded system will have that sensors or actuators by which they will sense the data or fetch the data from the outside world. Now once the data has been arrived or received, the firmware within it, in which we have written the set of instructions, will process over this data. They will decide that what part of the data are accurate and what is not, and based on the conclusive result they will deliver that particular output to another hardware or can say the external world. Now in our day-to-day life we see n number of embedded system examples. Let's say our smart watches, traffic signals, or automotive vehicles. All these embedded system examples, or can say this, all these systems have one thing in common, that they are supposed to do one specific job. They are independent of the human intervention. Let's understand this how. If we talk about the smartwatches, then they are not just used to give one specific information about timing, but they also monitor our physical activity. The sensors embedded within that will also sense our heartbeat, our speed, our motion, our steps, etc. etc. Correct? Also, it monitors the activity of our cell phone, which is connected over an network interface. So this is one common example where smartwatch is nothing but just a timing device which gives the timing information, but also a lot more than that. So let's talk about the traffic signals. In traffic signals, the embedded system is sort of timer based mechanism. They will allow user to identify that this is the right time to stop the car and this is the right time that I should be start my car. So these systems are reliable in order to have management in traffic signals where there is crowded traffic. The next is automotive vehicles. In automotive vehicles, let's think of a car. In car, we have, if we apply the brake, then the car should get stopped. If we give an accelerator, then car should increase its speed. If we change the gear, then there should be change in motion. If there is a case of an accident, then suddenly the airbag should pop out. So these are the decision making scenarios in which the embedded system plays a crucial role, and that is why they are real time of embedded system. Now we do have a question that what is the need of an embedded system? So let's understand that. Let's understand this with one example. Let's say I have one computer. In that computer, we can say it is designed to do multiple tasks at the same time, correct? Computer is supposed to do like sending the emails, allows user to enter the text, process that particular text, allow user to send the messages, allow various programs to be stored, allowed backup functionality to store contents and whatnot. Now I want a specific design in which my only purpose is to write the text, to process the text and show it on the display. With this simple application, do I really need the whole computer? Because my job is just one simple, that I wanted to do this particular task. It should be serving that entering and giving the information kind of application. So to solve this task or to serve this purpose, I don't need the whole computer or the CPU, general purpose unit in short. What I need is one particular device or the block of that particular CPU which is supposed to do this task. So can I pick that particular box or can say the hardware module and use it as an individual application? Yes, we can, and that is what embedded systems are, correct? They don't use the whole module, but they design as if we can use for that particular purpose or the task. And that is why they are less power consumptions, because they are doing one specific task rather than the all unnecessary jobs that is supposed to do. At one particular point of time, we are not bothered about another task. The application itself is made in such a way that it should be doing one particular job. That's it. Also, they are customizable based on our requirement, based on our applications. So that product which is finally made, that will be an application oriented. And on top of all of this, we don't require human intervention because whatever the decision that is being made will be done by the device itself. And who will be supposed to do that? Again, the firmware embedded within it. So this is why embedded systems are serving a very huge purpose compared to what the traditional computing system like our computer is serving. So when we talk about this application in a large scale of industry, we are more required to think about the power consumption, the memory consumption. And when we gather all those scenarios at that point of time, embedded systems comes out to be a very reliable options. So if we talk about the types of an embedded systems, then there are basically two main categories. One is based on the performance or the functional requirements, and the other based on the microcontroller. So if we talk about the real-time embedded system, then it is that particular embedded system is very time crucial. The time is the most important thing or the factor in this particular comes to decision making. So there are basically two parts. One is soft real-time system and another is hard real-time system. Hard real-time system is something which is we can think of like an airbag system in the car. For an example, if at one particular point of time, if airbag of the car doesn't pops out, then that particular system is not reliable, that functionally is not reliable. So here the timeline of that particular decision making must be met at one particular point of time. The another one is the soft real-time system. The example of it can be a microwave oven. So in microwave oven, definitely there are time specific tasks that is supposed to be done, but the time is not that hard deadline. User can have that configurable time. The second one is standalone embedded system. In this embedded system, it is very simple, less complex, where we can have one particular port, analog port, through which the output goes, through which the input goes, and within that particular system, processing is happening, and there is one specific output in terms of sound or trigger. For an example, we can have a doorbell. The third category is the network-oriented embedded system. In this system, two embedded devices are communicating over the wireless interface. We can think of all the IoT devices. For an example, smart home or smart farming, where these devices are supposed to transfer the data over an internet connectivity. The fourth category is the mobile embedded system. These are the very complex and high power consumptive devices we can think of like in laptop or mobile phones. If we talk about the performance based on the embedded system, the performance of the microcontroller, then there are various three kinds of system. One is small scale, medium scale, and sophisticated. The major difference between these three systems is the type of the microcontroller which is being used. It can be 8-bit, 16-bit, or 32-bit based on the scalability. Also, the power consumption of sophisticated embedded system is quite high because it's quite complex compared to the small and medium scale. And likewise, small scale has the minimum power consumption because they are the less complex devices. The example of small scale can be a robotic arm or electronic toys. Medium scale we can include washing machine or any home items. In sophisticated, we can think of the satellite systems which are used or our television. The whole diagram, modular diagram of an embedded system, then it will look something like this. Can we say that the microcontroller or microprocessor, they are acting as a bridge between the input and output? Of course, yes, because those are the main devices which are defined to do one specific decision making task, and which is very crucial in every embedded system. So this microcontroller will take inputs from either the sensors or either any action, and that action can be like switching on and off, or typing something through keyboard, or giving as an interrupt, or as a timer interrupt. So by that way, microcontroller within it will be able to decide that now is the time that I should be start performing this decision making activities. Based on the decision or the processing, whatever the data that it got, it will be delivered either through notification or through any display unit. A notification can be like LED or buzzer, or display unit can be like 7-segment LCD or graphic display. In order to perform this all the processing, they can also use various controllers to make the system more reliable with respect to time as well as hardware. So those controllers can be actuators, relays, switches or PWM. And within that, to process that data, they have that specified memory mapped input output registers within which the output data is stored. Now, if we talk about what is currently booming in the market with respect to embedded systems. So, like we said, in automotive industry itself, currently the self-driving or self-assisting mechanisms are being developed where there is zero intervention of human. Also, the safety mechanisms which we are having right now, they are also going to be improvised in a way that it is more reliable and more accurate. If we talk about the consumer electronics, then the washing machines or the microwave ovens that we had 10 years before and what we have now, based on the functionality, based on the performance, they have been improvised quite a lot. If we talk about the aerospace and defense sector, then the whole engine operation, temperature and speed control mechanisms, the weather forecasting, weather monitoring systems, all those require quite a lot complex embedded systems and the accurate ones. We have also made quite a development in that sector. If we talk about the healthcare, then currently we are having the medical devices by which we are able to diagnose a particular disease even remotely. We can cure a treatment without having on place and without being physically at that particular place. So that is quite a huge improvement, or can say the revolution that we are having with the help of embedded systems. Of course, in the telecommunication sector, we can see the revolution of mobile phones from touchpad or running on 2G or 3G. Now we have the smartphones which are running on 4G or 5G with quite complex mechanisms with multiple n numbers of services having provided. Also, one another sector that we can say is enhanced graphics, augmented and virtual reality. This is something that is unreal. Like if I want to have an experience of a Paris without being at the Paris, just staying at my home, I can do that. I can explore the Paris with the feeling that I'm actually there. Another example is like if I wanted to feel the presence of mine at my parents' wedding, then also I will be able to do that with the help of embedded systems. So these are very quite unique applications, or can say the experiences that we are able to get with the help of embedded systems. If we talk about what market looks like within this 10 years of duration, then current market value of embedded systems is 75.67 billion US dollars, which is expected to be raised to 159.12 billion US dollars. You can see that huge difference between these two figures, and the key players are expected to be well-known chip manufacturing companies like Intel, Microchip, Samsung. So we can say that the processor or the controller which are being used within these upcoming devices, which are supposed to be an embedded devices, will also be a high performance, high power, very self-reliant mechanisms or the devices. The growth rate of this particular field will be raised by almost 8%. The surge in the demand for the electronic vehicles and hybrid vehicles are increasing with the innovation of various high powered processors and controllers. Also, the embedded systems are working on particular network interfaces. So whatever the threats that we are having right now regarding the security, that threats will also be gonna there in that particular embedded system when it comes to networking. So right now we are also focusing on the part where we give more self reliable, or can say the more accurate security proof system compatible with the network, reducing the less cyber attacks and all the security breaches. Also, we are having the advent of 5G, which is supposed to boost the whole IoT system. We will be going to talk about that a bit, about that particular IoT system in upcoming slides. Also, the augmented, like we said, augmented and virtual reality, which are the rising trend of embedded system. There are also that is also going to be expanding upcoming years. So let's talk about the embedded devices in Internet of Things. Now we do know what are the embedded systems. So this whole circle indicates that this is an embedded system. Now what if one embedded system communicates with another over an internet? So this whole ecosystem or the environment is called nothing but the Internet of Things. The question is, why do we need that? Let's take an example. We are, of course, very lazy people, correct? I don't want to get up from my bed and turn on and off the light or fan whenever I want. So for that, what I invented, I'm also a smart people, right? So what I invented an embedded device which can communicate with the interface of wireless and can signal the other device that turn it off, turn it on. Another example is in farming, there is supposed to be a farmer on the field constantly to monitor the crops, to monitor the irrigation systems, when to start, when to stop, and all those tasks, right? What if I introduce one system which will do all the tasks which a particular farmer is supposed to do? It will monitor the crops. If there is any infection or the crop is not good enough, it will indicate the farmer. While farmer will be at his place, sitting in the room, and will be able to get all the information which is actually happening on the field. Also, that particular system will be able to start and stop the irrigation systems based on monitoring what is the actual water level inside my plants. So all these smart decisions that a human is supposed to take, now a machine will be able to take, and that is all because of these embedded systems. So these embedded systems talk with another embedded system or the device over an interface that is, of course, the wireless, that can be LAN, WAN, or any local connectivity interface, and over which they are supposed to communicate. So next, we do have a question that how we can learn the embedded system. What are the prerequisites that I'm supposed to have. So first is basics of electronics. One should be able to know the common things regarding digital electronics like various gates and flip-flops. Those are the main decision making elements which are supposed to play role in our embedded systems. Also we can have state machines which are supposed to identify the design of that particular, or can say design or behavior of that particular embedded system. The second thing is analog electronics. In analog we can have the information of various gates, various MOSFETs, various transistors, how the particular things behave with respect to various power conditions, what are the timers, how particular integrated circuit is behaving, and what can be used in order to implement particular analog hardware. Also, from the programming end, we can have the common language C, which is supposed to be used in embedded system majorly. But in complex embedded system, we can also find C++ as well as the Python programming languages. Also, apart from that, we should have a prior knowledge of microcontrollers and microprocessors, that how these two things differs from each other, when to use where, and what are the external peripherals that we can connect with this particular hardware, and how is the behavior of that particular controller or processor with that interfaces, how to operate those interfaces. Also, if we wanted to make a time critical system, then we have one real time operating system, or that is FreeRTOS. This RTOS will provide us various functionality in order time critical situations or the operating systems. Also, we have various communication protocols that we can learn of. Those can be wired or wireless. In wired, we have Ethernet, RS-232, SPI or I2C. There can be synchronous or asynchronous. In wireless, we have BLE, Zigbee, RFID, Wi-Fi, and all those protocols which we can learn. And most of the wireless protocols are used in IoT embedded systems. How we can make the most with our community VLSI chaps? You can be the part of our core team creating content. You can contact to @max_chap on Telegram. You can also learn VLSI better by subscribing our YouTube channel, VLSI Chaps. We are posting various valuable videos regarding various tutorials. To get all the information or question and answers or the materials, you can have our website vlsichaps.com. You can also interact or help others in our Telegram groups @VLSI Chaps and @VLSI_Chaps_channel. You can also read Quora Space VLSI Chaps. We are answering as well as questioning there. You can also follow VLSI Chaps on Facebook, Instagram, LinkedIn page, and Twitter, and also various platforms. You can help our community grow by sharing VLSI Chaps on our social media. As more number of helping hands will be, we can have a huge family. And likewise, we can have more opportunities and more learnings. You can also share job opportunities by keeping eye on our job opportunities group. So yeah, thank you guys. Thank you for watching this video. You can like, share and subscribe. See you in the next one.